This project is created for the subject of innovative product development under the mentorship of Dr. Kriti Srivastav and is created by Palka Dhiravani, Rajvi Parekh, and Tanish Kandoi.
In our project, we carry out solar radiation forecasting for determining whether using solar energy would be more cost efficient than using electricity for a given location. When we talk about why making this shift is needed, the answer is simple. Solar energy is renewable, which means we can never exhaust it. And this is going to solve a lot of problems as a majority of the population relies on coal and petroleum for the power generation, and these resources are depleting fast. Apart from all the environmental benefits of solar energy that we're all aware of, it has a major drawback, and that is its variable and uncertain nature. With our project, we aim to reduce this uncertainty by making forecasts about how much solar radiation a location will receive on a particular day and in a particular hour. There have been other research works before that have used various machine learning and deep learning algorithms like artificial neural networks, gradient boost, etc. There have also been research works that talk about using which input parameters and how many exactly would give the most accurate results. Moving on to the research gaps, our work builds upon these research gaps of the previous research papers, as mentioned in the slide. Next. Coming to the impact that our project is going to create, there are 17 fundamental objectives or goals laid down by the United Nations that serve as a call to action for all its countries to work towards for building a more sustainable future. These goals are called the Sustainable Development Goals or the SDGs. Our research project involves SDGs number 7, which is affordable and clean energy, as well as SDG number 13, which is climate action.
So the problem definition. In order to determine how advantageous and cost effective switching to solar energy would be for the local population, our study uses machine learning and deep learning models to forecast future solar radiation levels for a specific place and in turn tell us how cost effective would it be. Next, the cost estimation architecture. So first we do the data pre-processing in which we remove the outliers and missing values. Then we do the data visualization in which we make different correlation tables and much more. Then we apply ML algorithms like Era Boost, Random Forest, Arima and Sadima. And we take user inputs like the location, monthly electricity bill amount, monthly power consumption and the available rooftop area, which are fetched to the trained model. Then the model then forecasts the solar irradiance for the particular location, and by using the mentioned formula, it calculates the monthly savings in the electricity bill of the user. Then the breakdown period is also calculated for the user. Data selection. We have used the NSRDB dataset, the National Solar Radiation Database, which is a serially complete collection of hourly and half hourly values, which contains three different measurements, mainly the global horizontal, direct normal, and diffuse horizontal irradiance. We have taken four locations from India: Andhra Pradesh, Madhya Pradesh, Tamil Nadu, and Rajasthan.
So, coming to data pre processing and visualization, we made use of the following parameters in the dataset: year, month, day, hour, radiation, temperature, precipitation, humidity, pressure, and wind speed. On conducting a correlation analysis, we observed that radiation had a high correlation with temperature, humidity, and wind speed, and the rest of the parameters did not show any significant correlation with radiation. The main pre-processing steps involved were date-time format conversion. Here we converted the given day hour time into daytime format, which can then be interpreted by various time series models. We then split the dataset into day and night and got rid of the night hours. As you can see in the diagram on the right, radiation during the night hours is almost negligible, hence we only kept data from 6 am to 5 pm. Third, all the missing values were filled up using linear interpolation. We then plotted the various parameters to look for outliers. and the ones that had a considerable amount of outliers were removed. As we can see, temperature, radiation, and wind speed had quite some outliers, which were then removed from the data. As we can see, data was distributed over a day and month in the following manner for the state of Andhra Pradesh. The data was normally distributed over a day, and in the monthly distribution, the summer months, which are mainly May, June, and July, had the highest amount of solar radiation received. On plotting all of the data from 2017 to 2021, we could clearly see the repetitive pattern in the data. This was a strong indication that the data is seasonal in nature. On observing the spread of radiation over a period of a few years, we noticed that it has a repeating pattern. We then decomposed the seasonal data using the seasonal decompose model from the stats model library. This seasonal decompose function helps us decompose our time series data into trend, seasonality, and noise. Even here, we can clearly see that our data is seasonal and we can see a clear seasonal trend. Hence, we were able to conclude that our data is purely seasonal since we could extract the seasonal components on conducting a time series decomposition. Temperature, humidity, and wind speed showed a considerable amount of correlation with radiation, and we observed that the amount of solar radiation received is higher in the summer months as compared to the winter months. Hence, after visualizing and pre-processing the data, we finalized the following parameters for training the model. These parameters were radiation, temperature, precipitation, humidity, pressure, and wind speed. Now coming to the performance of the models that the data was trained on. So talking about the models chosen, we shortlisted 2 univariate and 4 multivariate as our well-performing models. LSTM networks address the vanishing gradient problem that makes network training difficult for long sequences of data. Gradients are used for updating RNN parameters and for large sequences of data. These gradients become smaller and smaller to the extent that effectively no network training can take place. LSTM networks help overcome this problem and make it possible to capture long term dependencies in sequences that are separated by a large distance. LSTM models can also help capture seasonalities over short as well as long periods. And this was the main reason why we chose LSTM as one of our training models. Coming to the seasonal ARIMA, which is also known as the seasonal autoregressive integrated moving average, which is a SARIMA model, it is an extension of ARIMA that explicitly supports univariate time series data with a seasonal component. It adds 3 new parameters to specify the autoregression, the differencing, and the moving average for the seasonal component of the series, as well as an additional parameter for the period of seasonality. Hence, we decided to choose LSTM and Sarima as our models, and Sarima ended up performing the best, having a mean square error of 1500 to 4000. Now, coming to the multivariate time series model, we use the gradient boosting, the random forest, the XG boost, and finally, we had an average ensemble of all the previous 3 mentioned models. And as we can observe, all of these models have a higher mean square error as compared to the previous Sarima model. And the average ensemble model was not giving a better accuracy as compared to the other 3 models. Hence, it was then concluded that the seasonal ARIMA model was the best performing model and gave us a forecast as shown in this diagram. The gray region in this diagram is the region of values having 95% confidence.
Coming to the second part of our project, let me show you an example of the cost estimation calculation considering the location of Andhra Pradesh. Next, where according to the forecast, approximately 600 kilowatt hour of solar power is generated. If we consider for a household the average power consumption to be 700 kilowatt hour, and in India, conventionally, a 1 kilowatt rating solar panel approximately produces 120 kilowatt hour of power. So, if we divide both of these values, for this particular household, a rating of 6 kilowatt solar panel would be required. And then if we consider 5.5 rupees to be the basic solar energy tariff, so since for solar energy only the additional units of power consumed are charged, so which is 700 minus the 600, that is 100 multiplied by 5.5, which is the solar energy tariff. My monthly bill for that particular household comes out to be only 550 rupees as compared to 3 to 4 thousands of rupees for a typical summer month. And so it can be very evident of how much money a particular household would save by making the switch to solar energy. Thank you.